Hello, welcome to Discussion 7 walkthrough for CS61B. Today we're going to be covering the first half of algorithmic or asymptotic analysis. Some announcements, and we can get into the review for the week. So first of all, in this class, we're going to be talking about a lot of things coming up, right? We're getting to the second half of the class. We're going to start talking about things like data structures and algorithms. And the question is, what distinguishes different data structures from each other than their structure itself? Like when we learn about hash maps versus tree maps, when would you use either? And the way we evaluate this is using the cost of each data structure or algorithm. And we care about two different forms of cost. One is called time cost or time complexity, and the other is spatial cost or space complexity. In this class, we're going to be focusing on time complexity in particular, but space complexity is something that we'll touch on when we talk about sorting algorithms. So the idea behind time complexity is how long does it take to run this program if we feed it in a certain input, and in particular, how does that time scale as our input gets very large? So we're not really caring about how long it'll take if we feed it like 5 versus 10. We're caring about how the time it takes for the program to run scales as we go from like 1,000,000 to 1,000,000,000 in the size of our input. The way we do this is, well, think about it. There's one way we can do it where we can sit in front of our computer with a stopwatch, but that has a lot of cons. Well, first of all, different people's computers run at different speeds. So that means that it would be difficult to find an objective way to measure this. If I measured it on my computer and someone else measured a different program on their computer, it would be difficult to tell if our computers were contributing to how long it took. Second of all, the problem is that if we care about these things at very large scale, if we care about that billion versus million inputs, it might take very long to run in real life, and we might not want to sit here and wait for that to happen. So we use math instead, and we specifically use something called asymptotic analysis. In asymptotic analysis, like I said, we care about as things get huge, so we ignore things like constants and we ignore things like lower order terms, which we'll see in the examples, and we only care about the speed with reference to the input that's usually defined as n, so we don't care about things that take a long time that are independent of that input. There's 3 bounds that we use. We use big O, which is basically an upper bound, and so this upper bound is not necessarily tight. It can be a loose upper bound, which basically means that, like, for instance, a big O of n squared upper bounds a lot of things. It upper bounds constant runtime, it upper bounds linear runtime, it upper bounds logarithmic runtime because it's slower than all of those things. The flip side of that is omega, which is the lower bound. And again, the lower bound is not necessarily tight. It just means that the program definitely runs as fast or slow or slower than the value that we're passing in. So something that is omega of linear time, lower bounds, something that takes n squared time to run. It lower bounds something that takes linear time to run. So it can be tight. It just doesn't have to be. And theta, this one's pretty special because it's the tightest bound, and this only exists when the tightest upper bound and the tightest lower bound converge to the same value. So there are certain functions where there is an element of randomness or something that is unrelated to the input that causes the upper bound and lower bound to be distinct from each other no matter what. There's no way to get those two to meet, but a lot of functions don't have that problem. And in those cases, the tightest bound for both the upper bound and the lower bound are the same value, and in that case we call it a big theta bound, and that's basically how fast the program scales. One thing to note is that there are some sums that you might want to know. Here's a sampling of some of them. There's others. The more problems you do, you'll get a better intuition on what sums are nice to have written down on your cheat sheet. I recommend you write down the geometric summation formula and the arithmetic sum formula at the least, and whatever else comes up as we go through these discussion problems. And here's a chart showing the complexity for different things. So down here at the very bottom, you can't even see it. It would be blue is constant time, which basically means the runtime of the program is completely independent of the runtime or the size of the input. So no matter how big your input is, it takes the same amount of time to run. That's constant runtime. And then we have logarithmic runtime, which is this red line. Then we have linear runtime, which is this green line. We have this purple line, which is n log n. We have this teal line, which is n squared. This orange line, which is n, or 2 to the n, which is exponential. And then we have this light blue line, which is n factorial. Let's get into the worksheet. So this time we are going to talk about what is faster, and keep in mind that it isn't always the case that we know for sure which one is faster. So what's happening is, let's say we have two functions, one that is bounded by the things in the first column and one that is bounded by the things in the second column, and you're being asked, can you guarantee that one of these is always going to be faster than the other? And if so, which one? I'll give you a chance to think about it, and then we can go over it together. At the same time, we can also think about why we need to assume that n is large in these cases. Okay, welcome back. So here we have a set of various function bounds. So the first one we have is theta n and theta n squared. This one is is the most straightforward because both of these are tight bounds. We know that the first function takes exactly n time or some constant factor of n to run, and the second one takes n squared time to run. And in that case, we know that n is always going to be faster because it's a smaller number. And the second one's where things get tricky. So here, both of these are lower bounds, right? So we know that it's that the first one is definitely going to be slower than n. The second one is definitely going to be slower than n squared, but we don't actually know where they are. For instance, the first one could have a true runtime of n factorial, and the second one could have a true runtime of n cubed. And that would be totally valid with these bounds, but then the first one would end up being slower than the second one. So there's no way for us to tell for sure which one is actually faster, because that depends on the situation. There's just no guarantees here. The next one has a similar problem where these are upper bounds. So even though this number is smaller than this number, which might make you think that the first function is going to be smaller or the first function is going to be faster, that's not necessarily the case because this is just upper bound. So maybe this is upper bounding. Maybe the true runtime of this function is theta n, and the true runtime of this function is theta log n. And in that case, both of these bounds would be valid, but the second one would be faster. So again, we have to say neither. Now here we have theta of n squared, so we know this takes n squared time, and this one takes O of log n time. So it's upper bounded by log n. Now log n is always going to be less than n squared, right? Because the speed of this is either log n or faster, and this is always going to take n squared time. So we know that the O of log n function will always be faster than the function that takes n squared time. And lastly, this one's a bit of a trick question because even though O is an upper bound and omega is a lower bound, which means that like almost all of the functions that they cover, this is going to be faster than this, there is that case that the actual true runtime of these functions could be theta of n log n for both of these, because both big O and omega are inclusive bounds. So it's like a greater than or equal to sign rather than just a greater than sign. So in that one case, then they would actually take the same amount of time. There's no way for us to know which one's faster, so we just have to say neither. And lastly, the reason we have to assume that n is large is because asymptotic bounds only make sense as n gets large, because it allows us to disregard constant factors and lower order terms. Otherwise, there's too much messing up. An example is the fact that I believe log n and linear, n squared is actually smaller than n when n is very small. If you zoom in on a graph, you'll see that n's like 0.25 squared is smaller than 0.25. And so these functions are not necessarily always bigger than one another, but as you get to a large number, they diverge from each other and they go in their respective directions. So we assume that n is large, first of all, to make it easier, and second of all, because we really care about the way that they change as we make the input bigger, not their performance at any specific input. Okay, let's do some more problems that are kind of like what we did before, except this time we're going to say, okay, this is something that takes x squared time, for instance. Is this upper bounded, lower bounded, or theta bounded by g of x? So basically, you're saying, well, if this is a bound, would this be above, below, or equal to that bound? I'll give you a chance to try it out on your own, and then we'll go over it together. Okay, let's go over it. So this first one is f of x squared, and this is g of x equals x squared plus x. And again, remember, we drop all lower order terms, so in this case, we drop this x, so they're both the same function in reality as they get very large. So this is a theta bound, because the upper bound and lower bound, because it's basically bounding it as tight as possible. For our next one, again, we drop all the coefficients, so we can just pretend that this is f of x equals x cubed, and this is g of x equals x to the fifth. Now, x to the fifth is going to be greater than x cubed as x goes to infinity, which you can tell by trying out x to the fifth over x cubed as x goes to infinity. You'll see that that goes to infinity as well. And so basically, in this case, we are going to get a big O. This is big O is an upper bound, and x to the fifth upper bound's x cubed. Next, we have f of x equals log x, and g of x equals 5x. Again, we can drop this coefficient, so this is just x over here, and x is always greater than log x as x goes to infinity. So it's another upper bound situation. X is upper bounding log of x. Next, we have e to the x and x to the fifth. Now, as x gets really, really big, e to the x is going to end up being much larger than x to the fifth. So this is lower bounding e to the x, which is why we have omega. And last, we have log of f5 to the x. Now, this might be a throwback to logarithmic rules if you remember them. But log of 5 to the x is actually the same as x times log 5. And in that case, log of 5 is just a constant coefficient which can be dropped. So really, f of x is equal to x, and g of x is equal to x. So this is going to be another theta bound. Now let's get some practice with actual code analysis. So the first one is going to be this example where we have this function. And remember that we are doing this based by counting the amount of constant time operations. So an example is that you can count the number of times this for loop runs based on counting the number of times that system.out.println is called, and same with constant k. And we're doing this in terms of n. So I'll give you a chance to try it out, and then we'll work on it together. Okay, so let's go over this together. So let's break this down piece by piece. We can look at this first for loop block first. So here, we can see that the first side of the for loop is going from 0 to n, and the inner for loop is going from 0 to I. So when I is equal to some x value, the inner for loop does x work. And there are kind of two ways to think about this when you're trying to figure out how this translates into runtime. So I have them both here. The way that I like to think about it is more graphical personally. So you can kind of imagine that as I goes up, the amount of work done also goes up by j. And that's when you get this triangle shape. So when I is 1, you get 1 work done by the inside for loop. When I is 2, you get 2 done. When I is 3, you get 3 done. When I is 4, you get 4 done, etc. And then you basically can take the area of this triangle, which is 1/2 n squared, because, I goes from 0 to n, and that gives you theta of n squared for this runtime. Another way that you can think about this is more mathematical. Well, the inner for loop does theta 1 work plus theta 2 work plus all the way up to theta n work. And if you know this, the formula for the arithmetic sum, which is something that I recommend you write down, that is n times n plus 1 divided by 2, and that will be equal to n squared once you get rid of all the constant coefficients in lower order terms. Either way, you get the same value. It's just whatever makes sense to you in your brain. So we know that this upper area takes n squared time. So let's look at this lower for loop. So this one, you just go from 0 to n. You're adding 1 each time, so you do 1 work for each of the n steps. So that's just going to be theta of n. Now for the full runtime of this whole function, we're going to sum up theta of n squared plus theta of n, and again, we're going to drop the lower order terms, which includes n now. And so we're going to end up with just theta of n squared as our final runtime. Okay, and that's our final answer here. So let's do another one. So I believe this is our last problem. So this is an example that calls another function. So we have cows go and we have bars arranged. As you can see, bars rearranged calls cows go. So I recommend you take a look at this and figure out what the final runtime is going to be. Okay, let's go over it together. So let's talk first about this kind of triple for loop thing going on up here. So if you notice, this whole for loop is actually independent of n. So I goes from 0 to 100, j goes from 0 to I, and k goes from 0 to j. None of this is dependent on n in any way. So no matter how big n gets, this for loop will still run the same amount of times. This means that the actual runtime of this for loop is just constant because, again, it doesn't scale with the size of the input, which is all we really care about. So with that in mind, we know that cows go takes constant time to run, and we can use that to analyze this double for loop we have down here. So this time it's easier just to do it with math completely. So we start with I equals 1 and you go to n, and this time we're multiplying by 2. We're not just adding 1. And the inner for loop just adds 1. So if we sum this up, we get 1 plus 2 plus 4, etc., plus n divided by 2 plus n. And if we put this into a summation, we get from 0 to log n of 2 to the I, right? Because we're multiplying by 2 every time, and we're stopping at 2 to the log n, which simplifies to n. If you didn't know, the summation of a bunch of powers of 2 is actually equal to 2 to the whatever plus 1 minus 1, which simplifies again when we get rid of all of these extra terms to just n, because we're going from our final value 2 to the log n. And that you can get rid of the exponent and the logarithmic here. This is a summation that is great just to write down. It's just great to know generally. You'll see the summation happen a lot when we look at recursive calls because we'll see a lot of this powers of 2 happening there as well. Okay, and then our final answer is theta n, and that brings us to the end for today. So thank you and good luck with the rest of your week.